we're going to talk about using machine learning to detect fraud and how we can do that, kind of how the models work, what key aspects of the data we're looking at, and just generally kind of how to build any kind of machine learning model. So hopefully you get a lot out of this, and yeah, I'm happy to be here, happy to be talking about this. So yeah, like Aggie said, I'm the VP Data Science at Tixr. So a little bit of a plug for my company. Tixr is a live events ticketing company. So we compete with Ticketmaster, AXS, Eventbrite, all those guys. So in 2022, we sold millions of tickets on the system, 20,000 different events across 10 different countries. And we project those numbers to keep growing indefinitely, hopefully. And so we were founded in Santa Monica by 2 UCLA grads. And yeah, we're 10 years old now. So we're going to have a big 10-year party in May. It's going to be fun. All right, so here we go. I don't know if you guys have ever heard of Andreessen Horowitz, but they are a very large Silicon Valley investment firm. I think they're one of the top 5 biggest tech investors in the world. And they basically come out with this marketplace ranking every year. And if you look on the left, it's got the top 10. So some very big names, right? Instacart, Viagogo, Turo, StockX, almost household names. And on the right, we were lucky enough to be ranked number 25 this year. So that was a huge accomplishment for us. And it's just a testament to everyone's hard work and the kind of vision that we're trying to deliver the marketplace. So it's awesome that we're kind of getting the notoriety from the kind of public to see all the good work we've been doing. So they actually did a little segment, a little in-depth, detailed view of all the ticketing companies. So this again is the Andreessen Horowitz people. So basically, we're a primary ticketing company, which means we work directly with the vendors and the venues. So if you've ever bought tickets on StubHub or TickPick or Viagogo, those are secondary marketplaces. Those are resale. So if you scratch those off the list, and then Today Tix is a very small, like Broadway musical ticketing company, which it's not really what we do. So if you scratch those off the list, we are the fastest growing ticketing company on the planet right now, primary. So yeah, so we must be doing something right. So hopefully that keeps going. I like to think it's in no small part to my awesome fraud models, but that probably has nothing to do with it. We'll see. Okay, so here we go. The goal of this whole thing is, this whole enterprise is that we want to build a fraud detection model. Okay, so what does that mean? Well, think about when you buy tickets online, if you've ever bought concert tickets or sports tickets or anything. So when you buy tickets online, there's some basic info at the top here that we're going to know about the purchase, right? So we're going to know email address, birthday, name of the user, number of tickets, price, lat long, the year, month, day, hour, minute, second, timestamp of the purchase. So for this talk, I'm only going to be using this basic info. So I'm going to see how good of a model I can build with just the basics. Now, in reality, what we actually use is a lot more complicated of variables. Like we're looking at, number of unique IP addresses associated with the user. We're looking at VPN proxies. We're looking at name, email similarities, credit cards per account. So in reality, there's a lot more going on, but for simplicity's sake, I'm just doing the basic info here. Sorry. Okay, so let's look at, so we're trying to stop fraud in the ticketing company. Well, what does that mean? What does fraud mean when you're buying PDF tickets? So I made this grid to kind of display what's going on here. So at the top, we've got the 3 actors involved. We've got the fraudster who has person A's stolen credit card. And typically this happens to big data dumps on the dark web, right? Like you can go on the dark web and buy 10,000 credit cards for $20 or something. And maybe only 5% of them work. So there's this kind of seedy underbelly of internet fraudsters. There's Tixr, the ticketing company, and there's that sad person A who, unbeknownst to him, is going to get a big charge on his credit card. All right, let's step this down in time and we can see kind of how the fraud works. All right, so step 1. The fraudster is going to use that stolen credit card. He's going to buy $2,000 worth of VIP tickets. He's going to get those tickets emailed to himself. So all right, he's got the tickets. Tixr's got $2,000. Person A's got a $2,000 charge on the credit card. Okay. So the next thing the fraudster does is he's going to take these PDF tickets and he's going to sell them online somewhere. StubHub, TickPick, Craigslist, wherever. He's going to sell and say he just wants to sell them fast. So he's going to sell them for less than face value. So he gets $1,500 from the sale. And, you know, we get nothing. The person A that gets nothing there. Okay. So step 3, person A is looking at their credit card and notices, hey, I've got this $2,000 charge and I don't recognize this. So when you call your credit card company and you see a charge like that, you can say, yeah, this is fraudulent. And what they'll do is they'll initiate a chargeback. Okay, so you can charge back any credit card purchase as a consumer. So what happens is the bank or the credit card company just plucks that money back from Tixr, gives it back to person A, puts it back on their credit card. So at the end of the day, what happens here? Well, the fraudster gets that $1,500 from the StubHub sale. Tixr, we lose a little bit of money because of the chargeback fee, and then person A is no harm, no foul, right? So this is the basis of the fraud. This is why they do it. And if you think about it, if you were to buy something from like Nike.com, right, some actual physical item, when they mail it to you, that is kind of evidence of that de-anonymizes you, right? Like I have an actual house or PO box. With email addresses, you can just create fake ones all day long, right? So it's the fact that the item is digital that makes it a high fraud target. Okay, so all right. So now that we've got, you know, what is fraud in this industry? What's that look like? Okay, so that's kind of the problem space. Now, again, our goal was to build a fraud model, but just more generally, more basic, what is a model, right? So fundamentally, a model is just some function that outputs 1 or 0 in this case. All right, so it's just a mathematical function where we input the basic info variables and it spits out, hey, legit or hey, chargeback. All right, so what does the data actually look like here? So basically, we've got, how I built this model was I've got 50,000 orders, 700 or so are chargebacks, and 49,800 are legitimate. So chargeback is a rare occurrence. So basically, I've got, you know, from this information, I need to convert these strings. So for instance, like email address, name, I need to convert all this information to numerical data. Models love numbers. They don't know what to do with letters, right? So the key is we've got to convert all these different letter strings to actual numbers that we can feed the model. So I came up with this list here of 15 different variables. So we've got quantity, which is the number of tickets in the order. We've got average price, which is the average price. We've got hours, which is the difference between the purchase time and the event start date. We've got time, which is the hour of the day. We've got latitude, longitude, inchar, which is the number of the characters in the email address, email numbers, which is the count of the numeric characters in the email address, ratio, which is the ratio of those two, month, the user birth month, day, user birthday, year, user birth year, name length, which is the length of the full username, percent consonants, which is how often the user is typing in, or how often their name has consonant letters, capital, number of capital letters used in the user full name, and then the final thing that we actually care about is the outcome, whether it's legit or chargeback. Okay, so basically why these models are cool is that you just throw everything at the wall, right? So before I make the model, I don't know which one of these is going to be important or any. Maybe none of these are important. The idea is you just throw it, you know, a ton of numerical values at this model, and then as you'll see, it kind of builds the model and then tells you what was important. So as we go through this, I just want to kind of give you like, yeah, so this is just an example calculation of how this kind of thing works. So email address, keel21@gmail. So what is inchar here? So inchar is 7 because we're just counting this 7 in front of the @ sign. Email numbers, there's 2, and then the ratio is 0.4. Same thing with birthdays. So we're just converting those to numbers, and then the full name length, right? We're just counting the characters, we're counting the consonants, doing the ratio, and we're counting the capitalizations. Okay. So again, we're just taking these strings and trying to describe it with numbers. All right. So now the distribution of two different populations, right? So we've got the good orders, legitimate orders, and then we've got the chargeback orders. So I thought just looking at kind of the distribution, maybe we can kind of guess on maybe some of the variables importance that the machine learning models are going to be picking up on. So this can kind of give you a good idea, right? Let's look at quantity. So typically people buy 1 ticket or 2 tickets or 3 tickets or 4 tickets. And green is the legit customers. But look at chargeback, right? Look at the fraudsters. They're buying 6, 7. Most of their tickets are this 6 or higher. And so, maybe you might think, all right, that probably could be important. Okay. So I'll just run through some of these distributions really quickly and tell you highlight some maybe interesting cases here. So let's look at time of day, right? The fraudsters, they're buying at like weird hours of the night, 3, 4, 5 a.m. And then the normal people, at more normal times. All right, we'll keep going. So location doesn't look like there's anything too important here. What's I thought was interesting is like the ratio, right? So it looks like very high ratioed numbers to letters. And so I was kind of looking at some example cases. There are a few fraudsters whose email address was like 178335570@gmail.com, right? It's like, so it's kind of picking up on that aspect of it. Because again, these people don't want to be caught, right? They want to anonymize as much as possible. And what better way than just to have an email address of all numbers? Okay, so we'll keep going. So interesting enough look at the birthday and birth month. So we would expect just a general uniform distribution as we would see in the green here. But look at the fraudsters, right? They're just typing in 010203, 010203. So they're just doing quick keystrokes, or they're picking the top one of the drop-down menu, right? So they're not doing any real, like fraudsters are very rarely like clicking down to September and then clicking 25th to put in a fake birthday, right? They're just clicking the fastest one. Okay, and then yeah, same thing with like, so what's interesting here is the capitalization. So normal people, either they never do caps or they do like their first name, last name. So it's a big spike on 2. Whereas fraudsters, they're very rarely doing any capitalization. So again, they're just typing in fake names, right? They're not taking the time to do like shift, the first letter, fake name, shift, last letter, fake name. So we're taking advantage of their kind of sloppiness in a way compared to the normal population. Okay, so yeah, all right, so you guys have a general idea of kind of what's going on here. We're just literally taking this, so a single row of data here is going to be a single order. So for every order, we've got all these different data points. And what we're going to do is just, throw it in the model and see what the model spits out. Okay, so this slide right here is the whole presentation. So I'm going to go over it very slowly and very deliberately. Okay, so we're building a model. So we're going to take our data set and we're going to break it up into a training data set and a testing data set. Okay, so I did a 70-30 split here. So I just randomly select 70% from the data and set that aside. And then I do this, the rest of the data gets set aside as the testing data set. Okay. So we're going to do a training data set. And then, so remember earlier I said a chargeback is a very rare occurrence, 1%, right? So we've got 99% legit, 1% bad. So the way that these models work is that all the literature and all the theory says that your classes should be more balanced than that. So 99-1 is not a good balance ratio. 50-50 is obviously the best balance ratio. And so there's these different techniques that we can do to get us to close the gap in the balance of the classes. Okay, so I'm going to talk about this in detail, but basically I'm taking the training set, I'm making 5 different kinds of copies of it, and then each one of those sampling training set data, I'm then sending it through 3 different model types: logistic regression, k-nearest neighbors, and random forest. Where in this process, I'm doing some cross-validation, some hyperparameter tuning. And at the end of the day, I'm going to get 15 different models, right? So I'm going to get like the log model that was made from standard. I'm going to get the k-nearest neighbors that was made from the downsampled. So I'm going to have this big family of models, 15 of them. And then I'm going to grade every one of them using the testing data, right? Because the testing data, I actually know what the outcome was. With this model, I'm going to generate what the model thinks the answer is. And then I'm going to compare the two. I'm going to grade them. And then I'm going to choose the very best model. And yeah, may the best model win. Okay, so yeah, so again, kind of what this looks like in more simple terms. I'm gonna use the training data, testing data. I'm gonna build a model. I'm gonna use the model to give a predicted answer, and I'm gonna compare that answer to the actual answer. So pretty simple, right? Okay, so a little bit on the different sampling types. So basically, the standard data set, I'm doing no special sampling. I've just got 35,000 orders, 500 chargebacks, nothing special there. For upsampled, what I'm doing is I'm taking the legitimate orders as the standard or as the number that I need, and then I'm going to resample the chargebacks until I get a 50-50 split. So I'm just going to keep oversampling this 496 over and over and over and over until I get a nice balance here. Similar concept with downsampled, except I start with the chargeback number and then I downsample the large 34,000 data set. So I'm just going to pick 496 points randomly from there. Now, SMOD and rows are more complicated. You can read the Wikipedias about them if you're super interested, but they're just this way to generate artificial data points using the underlying data. So those are just two different common methods to do this. Okay, so now that we've got all of our samples, we're going to build our 3 different models. So I'm going to talk a little bit about the underlying theory of logistic regression, k-nearest neighbors, and random forest. All right, so logistic regression, the way that it works is we're literally just, it works just like regression, y equals mx plus b, except there's more variables, and each one of those variables is not just a single number, but a vector of numbers, okay? So basically, we just plug everything in, have the computer calculate the best regression with the lowest residuals, and those are the numbers that we take. So it's literally, so z equals w naught, and then the summation of the weights times the vectors. So these are literally just numbers, right? So at the end of the day, it's just going to be like 0.2 times x1 plus 1.2 times x2 plus 0.6 times x3. We're just doing like some very basic modeling, and then we're going to feed that through this function here, which is the logistic function. So this just assures that we get from 0 to 1 as an outcome. So yeah, so what happens if we run that? Well, we run that and we get, you know, some model, some weights, correct weights, and then so basically what I did here was I just did like a sample calculation where we throw all these numbers in from our test set, we get a z-score, we throw the z-score in here, and then we get a probability outcome. So if this y hat is greater than 5, we say, hey, that's a chargeback. If it's less than 0.5, we say, hey, that's a legit order. So we go through and we grade all the ones in the test set. And that's that function. All right, on to the next one, k-nearest neighbors. So this one is a pretty basic model. So all we're doing is plotting the legit and the chargeback data points. And then for every test point, we're just saying, what is the nearest k neighbors, right? So for example, this is just a 2-dimensional space where we've got the test set here. And so if k equals 3, what I'm saying is, what's the 3 nearest neighbors? So what I do is I calculate a Euclidean distance between all these points, and I take the 3 closest ones, which it's easy to see in a 2D field. And I say, and I give each one a vote. So it's n equals 3. So 2 were chargeback, 1 was legit. So I would say, I would diagnose this test point as chargeback. Now, what if k equals 5? What if we say k should be 5? In that case, the circle expands and we count the 5 nearest ones here. So we get 3 legit and 2 chargebacks. So if k equals 5, this would tell us that this test point is a legit test point. Okay, so, but in real life, we're using, or in this model, it's not a 2-dimensional space, it's 15 dimensions. So we can't visualize it, but luckily for us, Euclidean geometry works. Euclid was a genius. So basically we can calculate in 15 dimensions, just a single number per distance. So we just do this again for this 15D space, and we get, at the end of the day, we just get some vote, and the vote is, yep, legit or chargeback. Now, what should we make the value of K be? Well, we just let the computer tell us what the best value should be. So that's called hyperparameter tuning, and I'll go into detail, a little bit more detail in a second. So now, random forest is a little bit more complicated. So it just, basically the way that it operates is that it creates 10,000 trees, so decision trees. I don't know if you guys have seen those, but basically you're just building kind of these basic rules like, oh, if it's greater than 0.5, it should be categorized as this. If it's less, categorized as this. So you're making these really dumb, simple rules to try to classify what these test points should be. Now, the hyperparameter that's tuned here is going to be how deep your tree should go. So remember, we had 15 different variables. The way that random forest works is that it samples only, so if the tree depth is 1, it's only going to sample one of those 15. So it's going to build, tree 1 is only going to randomly sample one of the variables. The next tree randomly sample one of the 15 variables, et cetera, et cetera. Now, if we do a m try equals 2, that's going to make a 2-level tree, so a depth of 2, and in that case it's going to sample 2 of the 15 variables and then build decision trees from that, and so on and so on. And so at the end of the day, you've got these 10,000, individually they're all not great fits, they're not great decision trees, but again, if you have a lot of them and then you just have it vote, somehow the magic emerges and it's right a lot of the time. So basically you let every tree vote, and then you take the final class. So similar to how K nearest neighbors was, in the sense that it's just doing majority voting. Okay, so again, how deep should you make your m try be? How deep should the trees be? And again, we're going to let the computer do all that work for us. So it'll tell us what the best value of that is. All right. So here we go. We've got this idea. We've got our 5 sample data sets that we're going to train. We've got these 3 ways we're going to train them. And now we're going to do tenfold cross-validation and hyperparameter tuning so we can get the right values for the K and the right values for the M try. Now, what is the point of cross-validation? Well, it's the classic problem in model making. If you make your model too general, you underfit, in which case the model isn't specific enough for your data, and so it doesn't describe it well. At the polar opposite of that end is overfitting, and that is you're fitting every little wiggle of your function and you're fitting it too much to the data. It's too specific. There's no way that the real test data is going to be exactly like this. And so this is the constant battle for time immemorial for these models. It's like finding the right balance between underfitting and overfitting. And so there's these different techniques that will, try to get us an answer that's somewhere in the middle. And that's what cross-validation and hyperparameter tuning are all about. Okay, so let's talk about cross-validation. What is that? Well, remember, we're dealing with we're dealing with the training set now, the standard training set. But you can do this very clever thing where you break that up into 10 different sets where you treat a 10th of each of the sets as another test set, right? So then what you do is, instead of having a single model train on all the data, you basically do 10 models and then average it. So you're finding, like, on average, what's the best. And so what this does is that it increases your generality, right? Because if you were to not do this, you would be super overfitting to all 10 parts of the data. But by varying a little bit at a time, you're trying to capture enough generality that you're making a good model, a robust model. And then we're going to hyperparameter tune again, and then we're going to, so basically the computer is going to try all the different K nearest neighbors, all the different Ks, and then figure out what's the best one to give me the best average answer from all of my cross validations. So it's kind of solving 2 problems in one series of codes. So again, we do that for all the different 5 different samplings. So, and it's going to be different for everyone, right? So for the downsampled, the actual magic number is 9, whereas before the number was 19. So again, the computer is just picking what the best one is. Same thing with hyperparameter tuning. So for the standard data set, same thing for hyperparameter tuning for the random forest. So we're going to let the computer do the tenfold cross validation. It's going to figure out how deep the trees really need to be. And so for the standard model, the standard sampling, it shows us that it should only be 3. So the best model is the one that randomly samples 3 of the variables and builds the trees out of those. And then we go down and we look at the downsample training set. And for instance, this one's 7. So this one needs 7 to give best results. All right. So after we built those models, what's really cool.
Quick question.
Yeah.
Question in the chat. What is the justification to select 3 algorithms?
Oh, it was, so I did this for my thesis at UCLA, and it's honestly just a bit random. Like I actually also did a support vector machine and a neural network, but I was just too lazy to type up all the results. And my thesis advisor said 3 was enough, so I stuck with that. But yeah, I mean, you can solve this problem with 10,000 different algorithms. And yeah, I mean, it would be interesting to do that and see which one is truly the best. So yeah, that's a good question. Yes, sorry, I can't really see the chat, so just stop me if one pops up.
Sorry, I have one.
Okay, cool.
It's related to underfitting and overfitting.
Yeah.
I did not really understand how do we determine if it's underfitting, overfitting.
Yeah, so you don't. Okay, so like you don't really know. Like let's look at this hyperparameter tuning, right? So basically, when k equals 3, it essentially was. Like your results are not going to be as good, right? So I think there may be techniques to tell me exactly if it's under or overfitting, and that's the issue here. So I can't tell you off the top of my head how to tell if the model is over versus underfitting, but basically from this you can tell that that particular model is off by either overfitting or underfitting, and you try to find the best ones. But I'm sure there's literature and functions that can tell you if it's over or under exactly.
Got it. Thank you.
Okay, so one of the cool things about some of these models is that not only do they, not only can you tune them and have the computer do all the magic, but they also tell you what was important going in, like what were the important variables and which ones were most important to the outcome, how we're determining the outcome. So what's pretty interesting is that if we look at the random forest, so quantity, cap, and average price, those were the top 3. And we look over here at logistic regression, quantity, cap, and average price, those are the top 3, okay? So there's something about these 3 variables that is really kind of where the meat and potatoes are of this problem. And then if you look at the bottom, so the least important were time, longitude, latitude, and hours. And we look over here, it's longitude, constants, latitude, time. So I feel confident that the models are kind of picking up on the same, the same things in reality that are actually happening. So that's just kind of a gut check. And it's kind of a cool feature of these models is that not only do they do all the work for you and solve the problem for you, they tell you exactly what was the thing that was driving the whole answer. Okay, so we're back here. We did our cross validation. We did our parameter tuning. We've got all 15 of our models ready to grade. So we throw them into the confusion matrix and we grade them. Okay. So there's, yeah. So basically we've got the case where like in actuality, it was a chargeback, and in actuality, it was legitimate. Okay. So we've got those 2 dimensions on top. And then on this dimension, we've got, what did the model predict the answer to be? Okay. So you can be right in 2 ways. You can be right because the model said chargeback and reality said chargeback. You can be right in the other way, which is the model said legit and reality said legit. And then you could be wrong in 2 ways, right? You could either, the model thought it was chargeback, but it was actually a good order, or the model thought it was a good order, but it was actually a chargeback. Okay, so there's all these different grading criteria that you can use to judge your model in that particular case of importance, right? So there are some instances in the real world where like you could stomach some false positives more than false negatives. But there's other cases where like you can only stomach the false negatives and not the false positives. And so it just depends on, there's not a magic bullet in terms of what do I maximize for here from this grading criteria. It just depends on your problem set specifically. And so yeah, you just kind of use all these in conjunction and then figure out what really is the most important thing that you want out of your model. So basically, here's all 15 of the results of all 15 of our models. And the random forest on the standard data set was actually the best one. Like, contrary to all the literature that said I need to change my sampling techniques, it turns out they were wrong. And it turns out I did all that extra work for no reason, because the standard one was the best. No, it was a good exercise though. And it's interesting to try to understand why that is the case. But basically, standard random forest was the best. So I want to go into a little bit more detail and try to give you guys like kind of what this means, how good this model was, okay? So on the test, so first of all, it blocked 140 of the 212 chargebacks, which is quite a lot, right? 2/3 reduction in chargebacks, and it only cost 14 legitimate orders. So I was super surprised by how accurate this model was, actually, by how limited of data that we really gave it. So basically, it was 15,100 orders, 14,951 legit, and 212 chargebacks. Okay, so let's look at the 14,951 legit. All right, so the model got 14,937 of those right. So it said it was good and it was actually good, but it said 14 were bad. And those 14 were actually good, okay? But that's still great. That's like 99%, 99.9% that it let the good ones through. Now, the other way, so there were 212 chargebacks, which are the bad orders. So it got 140 of those right, but it let 72 through. So we're not gonna be able to stop all fraudsters, all chargebacks, but to be able to reduce it by 2/3, that is quite a good model. And it costs such little, we're only losing 14 orders, legit orders. And so that's like a really good balance. And so we would totally recommend, turning this model on for all of our clients. Yeah, so that's pretty much it. That's all I had for how I built this model. So kind of like the next phases. So if we really wanted when we want to put this thing into production, basically, we've got to put this thing on an AWS instance somewhere in the cloud. And then anytime somebody tries to buy the ticket, and this whole thing takes like 50 milliseconds round trip. So it sends all of the customer's data to our AWS, to my model being hosted on AWS. My model crunches it out, sends back to our main server. Hey, is this a 1 or a 0? If it's a 0, we let the credit card process. If it's a 1, we block it. And the fan, it just says, sorry, your transaction didn't go through. So yeah, that's kind of how they work. And that was my presentation.
That's so cool. Thank you so much, Kjell. We're gonna open it up to questions, and we have the first one in the chat now. So Vitaly is asking, how do you know that the 140 are actual fraud?
Oh, sorry, say that again.
How do you know that 140 are actual fraud? I think since it's from your like training data, right? Or from your test data.
Yeah, so because whenever chargeback happens, the credit card company sends a signal to our database, and our database knows, in fact, this thing got charged back, or in fact, this didn't. Now, there is the case where like legitimately someone might charge back and it not be fraud, right? Like maybe somebody buys a ticket and then is like feeling sick that day and it's just like, oh, I'll charge it back. So that's called friendly fraud. And they are actually abusing the system, but it's not in some kind of systematic way. And so it's kind of impossible to disentangle true hardcore fraudsters that are doing this en masse and this kind of friendly fraud case. And so in that sense, it's impossible to detect if this thing was truly fraud. But in the other sense, I 100% know this was a chargeback because the credit card company told me this was a chargeback.
Mhm.
Okay. So because I thought the data on the previous slide was the data after you put in place your model and actually checked.
Yeah, so what I used to check this was the test set. So let's look back here. So this was the 30% test set here that I'm using to check. And
Yep,
so
yep.
I know the answers to that already. I know that was either
Yep,
charged.
right, got it. I just mistaken the last slide. I thought that was after you applied this model to actual purchases. Well, okay.
Sorry, yeah, I applied them to, so that is a good question, right? If I put this thing in the wild, how do I know that I'm not stopping bad purchases or good? How do I know that my model isn't being too aggressive and stopping good purchases?
Yes, exactly. That was my concern.
Okay, so basically we have a fan support hotline or chat or whatever, or email. So if a fan is being blocked over and over and they really want to go to this concert because they're true fans, they'll reach out. And they'll reach out and they'll say, hey, fan support, like it keeps blocking me. And so basically what I'll do is add their email to the whitelist. So the whitelist is the first line of logic that says, is there an email in the whitelist? If it is, let them purchase and don't run this model. What we found is that fraudsters don't want to reach out, right? They don't want to be detected. They don't want to give up their email address or have any records of them calling. And so it's just an asymmetry of like, if we're blocking good people, they'll reach out and then we can unblock them. Whereas like, if we're blocking bad people, they never reach out to try to be unblocked.
Yep, that makes a lot of sense. Thank you for clarification.
Yeah, good question.
There was another question in the chat. When deployed, will this be able to learn?
Yeah, so that's a good question. So yeah, so we've got to, for any of these models, right, you've got to constantly retrain and retest and do this whole process. This isn't a one and done. This is like, I got to do this once every 3 months. So fraudsters are always like, think about this model, right? It was blocking people that were putting too many numbers in their email address or doing something else. So fraudsters are always going to try to outwit you. It's cat and mouse, right? So maybe they'll get smart and realize like, oh, hey, like, I shouldn't be using so many capital letters, or I should use less numbers, right? So they'll try to get around the system. And maybe they'll be like, oh, it keeps blocking when I try to buy 6 tickets. Maybe it doesn't block when I buy 2 and 2 and 2, right? And so fraudsters are always trying to get around this, and I'm always having to retrain with the new data, and it's cat and mouse, which is great for job security.
Sorry, I have
Jared,
one
go ahead.
question. So what
sorry.
you're showing on the screen, that's the output of the random forest, right?
Yeah, go back to random forest. This one?
Oh, no, the screen that you were sharing where you showed like 66% was predicted correctly. So 66% is for the random forest, right?
Yeah. Mm-hmm.
Okay, thank you.
Mm-hmm.
Jared, go ahead.
Hey, Agnes mentioned at the very beginning that you were a very early team member for Tixr. Yeah. And I always love asking this question. If you could go back to, Kjell that just started at Tixr and tell him one thing, like to help him out in his journey, what would you go back and tell him?
Oh, good question. Probably get more sleep. Yeah, it's not a technical thing. It's just have healthier habits, get more exercise, get more sleep. That's honest. That's the honest answer.
That's great. Yeah, I love to hear that. Also, incredible talk. That was
thank
so
you.
good.
No, thank you very much. Thank you. Yeah, appreciate it. I'll also, so this is based on my thesis, and I will send the link of my PDF, and it probably goes into more technical detail if you guys are super interested. But yeah, thanks for the question.
Michael, go ahead.
Hi, that was a great talk, by the way, I agree. Was there any reason for the choice of the 70-30 split for the training and the prediction, or?
No, I mean, that's kind of like, if you just read blogs and stuff, it's usually like 80-20, 75-25. I just, but actually that's sort of a parameter you could sort of think of as tuning, right? It's like, you could do this same thing, but with 80-20 and then 75-25.
Okay, I see.
So you could basically you could basically tune every parameter and create more and more parameters, right? So that's something like, yeah, you could definitely do that. And maybe the 80-20 split's better. Who knows? Yeah,
Okay.
it's kind of random.
All right, thank you.
Question in the chat, whether you'd also be open to share the code for this implementation.
That's a proprietary Tixr information, but I will say that scikit-learn in Python, or I think there's a new framework in R. This is like, I mean, it took me a while to figure out what variables should be in and this kind of thing. But once you have that knowledge, like I could literally build these models in a day. Like you can crank this stuff out super quick, and it handles all this stuff for you, right? You're just like, okay, tuned hyperparameter.random forest, and it does all the magic.
That's
Yeah.
so cool.
So it would, yeah, you guys could literally do this in a week, I'm sure, if you had all the data.
Going back to the previous question about, how this is basically a cat and mouse game with the fraudsters, do you feel like there's also sort of a social scientist aspect to your work where you're, I don't know, learning about like different types of fraud, like from not a mathematical standpoint, or,
Yeah.
or is that a
No.
different team? Yeah.
No, that's a good question. Basically, yeah. So to catch a fraudster, you have to think like a fraudster. And so I find myself like, I guess I was just sort of naturally like this anyways, a little bit. But if ever I'm given like a rule or see a rule, I'm always subconsciously thinking like, how can you get around that rule? And how can you get around the rule and not get caught? And so that has helped me with this problem, because you just have to put yourself in the mind of somebody who's like, all right, I want to steal a credit card, and then I want to buy $20,000 tickets. And then, so that's definitely helped me. And to be able to, put yourself in different people's perspectives, definitely helps with solving this problem.
That makes sense.
Yeah,
Right,
but
any
it's also really great, just like morally, right? Like there's a lot of companies where you're just like, whatever, I'm doing data, and it doesn't really matter, and it's like it's not really good or it's not really bad. This, I feel like I'm actually doing good because I'm stopping a bad guy. So yeah, I feel like
it's like data superhero.
yeah, I feel a moral spike, like I'm doing a good thing to somebody somewhere.
Cool. Well, it's been a pleasure having you, Kjell. This is
Yeah, it was really fun, guys.